Psalm 16. Keep me safe, my God, for in you I take refuge. I say to the Lord, you are my Lord. Apart from you, I have no good thing. I say of the holy people who are in the land, they are the noble ones in whom is all my delight. Those who run after other gods will suffer more and more. I will not pour out libations of blood to such gods or take up their names on my lips. Lord, you alone are my portion and my cup. You make my lot secure. The boundary lines have fallen for me in pleasant places. Surely I have a delightful inheritance. I will praise the Lord who counsels me. Even at night my heart instructs me. I keep my eyes always on the Lord. With him at my right hand, I will not be shaken. Therefore my heart is glad and my tongue rejoices. My body also will rest secure, because you will not abandon me to the realm of the dead, nor will you let your faithful one see decay. You make known to me the path of life.
To understand why the Estonia was so vulnerable, we must first examine the geopolitical and economic currents of the early 1990s. Following the collapse of the Soviet Union, the Baltic Sea transformed from a barrier into a bridge. The route between Tallinn, Estonia, and Stockholm, Sweden, became a vital artery for a newly independent nation reconnecting with the West. The MS Estonia, originally built in 1980 as the Viking Sally, was purchased to serve as the flagship of this connection. She was a vessel operating under immense pressure, the pressure of national pride, and the crushing economic pressure of the ferry industry. In this high-margin business, the defining metric is turnaround time. Time spent in port is money lost. This economic reality drove the adoption of the row-row, or roll-on, roll-off design philosophy. Unlike traditional cargo vessels, where goods are crane-lifted into compartmentalized holds, a row-row ferry functions essentially as a floating bridge.
You have given me the heritage of those who fear your name. Increase the days of the king's life, his years for many generations. May he be enthroned in God's presence forever. Appoint your love and faithfulness to protect him. Then I will ever sing in praise of your name and fulfill my vows day after day. Psalm 62. Truly, my soul finds rest in God. My salvation comes from him. Truly, he is my rock and my salvation. He is my fortress. I will never be shaken. How long will you assault me? Would all of you throw me down, this leaning wall, this tottering fence? Surely they intend to topple me from my lofty place. They take delight in lies. With their mouths they bless, but in their hearts they curse. Yes, my soul, find rest in God. My hope comes from him. Truly, he is my rock and my salvation. He is my fortress. I will not be shaken. My salvation and my honor. Depend on God. He is my mighty rock, my refuge. Trust in him at all times, you people.
The safety of the entire vessel relies on a single premise, that the vehicle deck remains dry. Because there are no internal walls to stop water from spreading, the ship's watertight integrity is entirely dependent on the outer shells, specifically the massive doors at the bow and stern. The Estonia was built on the assumption that these doors would never fail. To understand the mechanics of the disaster, we must strip away the outer plating of the Estonia's bow and expose the machinery that governed her interaction with the sea. This brings us to the vessel's most critical mechanical assembly, the bow visor and the loading ramp. In 3D reconstruction, we can see the sheer scale of the visor. It was a massive 55-ton steel structure shaped like a medieval knight's helmet, hence the name. It formed the hydrodynamic nose of the ship. To load vehicles, hydraulic actuators would push this 55-ton shell upwards, allowing the inner loading ramp to be lowered onto the quay, bridging the ship to the shore. Crucially, the Estonia utilized a two-barrier system. The visor was the first barrier, designed to deflect the impact of waves. The ramp, located just behind it, was the second barrier, serving as the watertight seal for the car deck. On paper, this redundancy seems sound. If water breaches the visor, the ramp should keep the ship dry. However, a closer inspection of the blueprints reveals a fatal integration in how these two components were secured. The visor was held in place by a system of 3 locking points, 2 manual side locks, and 1 primary bottom lock, known as the Atlantic lock. When we zoom in on the Atlantic lock, the fragility of the system becomes terrifyingly clear. This device was situated at the very bottom tip of the visor. It consisted of a hydraulically operated steel bolt that slid into a socket welded to the forepeak deck. This single steel pin was the primary component resisting the upward and backward forces of the sea. Engineering analysis of the lock's metallurgy and geometry reveals a disturbing discrepancy. The Estonia was originally built for the sheltered waters between Sweden and Finland, the archipelago routes where wave heights rarely exceed a few meters. But on the open Baltic, waves can generate impact forces of hundreds of tons.
The Atlantic lock was designed to withstand significantly less force than the Baltic Sea was capable of generating. It was, in effect, a fair weather mechanism operating in a deep water environment. But the most catastrophic design flaw was not the weakness of the lock itself. It was the physical relationship between the visor and the ramp. In this cross-section of the bow assembly, we can see a rigid steel structure on the top of the rampa box housing. When the visor was closed, a mating part of the visor fit inside this box. This was designed to mechanically lock the ramp in place when the visor was down. However, this mechanical connection created a deadly dependency. It meant the two barriers were not truly independent. If the visor were to be ripped off by wave forces, its geometry meant it would not fall cleanly away. Instead, as it tumbled forward, it would snag on the ramp's housing.
Essentially, the safety of the watertight ramp was physically tethered to the structural integrity of the visor. Finally, we must look at the nervous system of this machine, the bridge indicator panel. On the bridge, the officers relied on a simple set of green lights to confirm the bow was secure. These lights were controlled by position sensors, simple limit switches. The flaw here was in what the sensors were measuring. They monitored the position of the locking bolt, not the condition of the visor itself. As long as the bolt was extended, the light remained green. The system had no way of telling the bridge crew that the socket holding the bolt had fractured, or that the visor was banging loosely against the hull. The machine was failing, but the indicators signaled all clear.
1 o'clock hours, September 28. The Estonia is plowing through 4-meter significant wave heights, with individual rogue waves peaking near 6 meters. She is maintaining a speed of 14 knots. From a hydrodynamic standpoint, this is punishing. The bow is not slicing through the water, it is colliding with it. With every pitch of the vessel, the flared bow slams into the oncoming swell, generating impact forces calculated later to exceed 500 tons forces, far beyond the design limits of the attachment mechanisms we just analyzed. Inside the forepeak deck, the machinery is beginning to die. At approximately 0055, a metallic bang rings out through the ship structure. A seaman is sent to the car deck to investigate. He reports a sound like a heavy sledgehammer striking the hull. In our forensic reconstruction, we can visualize exactly what is happening at this moment. The Atlantic lock, that solitary steel pin, is being subjected to repetitive dynamic shock loading. The metal of the locking housing is yielding. It is suffering from low cycle fatigue. The steel is not snapping instantly. It is tearing, millimeter by millimeter, with every wave impact. The bang heard by the crew is likely the sound of the locking housing finally fracturing, rendering the Atlantic lock useless. The visor is now held only by the side locks and gravity. Crucially, on the bridge, the indicator lights remain green. The locking bolt is still extended, so the sensor circuit is closed. The pilots have no data to suggest the bow of their ship is disintegrating. 1:15 hours.
the breaking point. The Estonia pitches into a deep trough and slams into a massive wall of water. The force overcomes the remaining side locks. They shear off violently. Now, the 55-ton visor is completely detached from the hull. It begins to move independently of the ship. As the bow rises on the next wave, the visor does not. It tumbles forward over the bulbous bow.
This is the moment the deadly dependency seals the ship's fate. As the visor falls, its aft structure catches the top of the loading ramp. The mass of the visor, combined with the force of the sea, acts like a giant lever. It rips the loading ramp fully open. The watertight seal is broken. The Estonia is now driving forward at 14 knots, with her mouth wide open to the Baltic Sea. Water begins to pour onto the open car deck at a rate of tons per second. This introduces the specific physical phenomenon that kills ro-ro ferries, the free surface effect. When water enters a traditional compartmented ship, it adds weight, causing the ship to sit lower, but the vessel usually remains upright. However, on the Estonia's continuous open vehicle deck, the water is not confined. It is free to slosh from side to side. As the ship rolls slightly to starboard, thousands of tons of water rush to that side. This mass does not return to the center when the ship rolls back. It traps the vessel in a list. The center of gravity shifts drastically. The ship loses its righting lever. By 0120, the list is 15 degrees. Inside the ship, loose cargo cars, trucks, begins to shift, sliding to starboard and compounding the imbalance. The list rapidly increases to 30 degrees. At this angle, the main engines lose lubrication pressure and cut out. The Estonia is now drifting broadside to the waves, helpless. The intakes for the ventilation system, located on the upper decks, submerge. Water begins to flood the accommodation spaces, Deck 4 and Deck 5. The speed of the collapse is terrifying. By 0130, just 15 minutes after the visor detached, the ship is on her side, listing 90 degrees. The emergency generators fail. The ship goes dark. The radar at the Uto Island station shows the Estonia blip fading. At 0150, the stern rises. Air trapped in the bow compresses, and the MS Estonia slips beneath the surface, settling on the seabed 80 meters below. The machine has failed, and the sea has reclaimed the evidence. When the Joint Accident Investigation Commission analyzed the wreckage, the verdict was damning not of the crew, but of the machine's lineage. The engineering forensic report confirmed our hypothesis. The Estonia was doomed by a catastrophic mismatch between her design capabilities and her operational environment. The Atlantic lock, that single point of failure, was found to have a safety factor that was shockingly low for the dynamic loads of the open Baltic Sea. In engineering terms, a safety factor is the ratio of a structure's absolute strength to the maximum expected load. For critical hull components, this factor should be robust. Yet, analysis showed that in the storm conditions of that night, the forces on the visor were pushing the lock to its ultimate limit with every wave. It didn't fail due to a freak event. It failed because it was doing exactly what the math said it would do under those conditions. It yielded. Furthermore, the investigation highlighted a systemic failure in the certification process. The Estonia was operating with a coastal bow door design on an international open sea route. The bureaucracy of maritime classification had failed to flag the visor ramp interdependency as a critical risk. The sensors were deemed inadequate passive systems that confirmed a locked state but ignored structural integrity. The legacy of the Estonia disaster is written in the Safety of Life at Sea SOLAS conventions we use today. The tragedy forced an immediate global overhaul of ro-ro ferry regulations. The Stockholm Agreement introduced rigorous new stability standards, requiring that ferries be able to survive with significant water on the vehicle deck, a scenario the Estonia could not withstand. Today, bow visors are almost extinct on new builds. replaced by clamshell doors or heavily reinforced side-opening gates.
And critically, modern regulations strictly enforce the independence of the inner watertight door. It can no longer be physically attached to the outer shell. If the nose of the ship is lost today, the vessel stays sealed. The chain of dependency has been broken. The wreck of the MS Estonia remains on the seabed, a silent, rusting monument to the unforgiving nature of the sea. Her loss taught us that in naval architecture, efficiency can never take precedence over redundancy. We learned that a ship is only as strong as its weakest latch, and that 852 lives were the terrible price paid to rewrite the rules of maritime safety.